Hello and welcome to the week 6 extra exercises walkthrough video. This week we're taking a look at some more advanced types of functions as well as a deeper dive into data types. And this is the last one where I've had to patch together some content from different recording sessions as a result of our shift from semester to trimesters. And once again, we've done this a few times now. It'll still be that the chapters line up with the task sheet you've been given. So just, follow it through in that order and it'll all be fine. Enjoy the rest of the video. So starting at the start, this one's all about vector manipulations, this warm-up exercise. So we start with two vectors, A and B, and then we perform a whole bunch of manipulations to the vector C. And then we also have a bit of a challenge one down the bottom. So what I'm going to do is I'm going to type this up in MATLAB and we're going to go through it line by line to see how it's changing after each modification. So let's bring up a blank MATLAB page. So our first line is A equals 2 to 2 to 10, and our next one is B equals 10 to negative 2 to 1. So just to get an idea for what each of these is going to look like, A is going to be a 1D vector that starts at 2 and goes up in steps of 2 until it reaches 10. So basically the even numbers from 2 to 10. Meanwhile, B has this negative 2 step. So it's actually starting at its sort of maximum value and it's stepping down until it reaches 1. So it's going to look like this. Starting at 10, then going down by 2, then going down by 2 until it reaches sort of the number that's bigger than 1 but closest to 1. So in this case 2. So we've effectively created two one-dimensional vectors that have the same dimensions. So they both have 5 elements. So that allows us to do the operations that follow. So C is equal to A dot times B. So that's element-wise multiplication. So that means that each element of A and B is going to be multiplied together. So the first one is going to be 2 times 10 from there and there, which gives us 20. Then we'll have 4 times 8, which is going to give us 32. 6 times 6 will give us 36. And 8 times 4 will give us 32 again. And 10 times 2 gives us 20. So we kind of look at the first elements and multiply them together, then the second elements and multiply them together, then the third elements, and that gives us our resulting vector. We can also check this as we go, so I'll just check that I've cleared all my variables from earlier. I had not, but now they're gone. So if I run this one now, you can actually see the values of A, B, and C here, and you can sort of confirm that your thinking is right. So we can see that what we'd written down for all 3 of those is correct so far. So then we can move on to our next one. So C equals C plus 2. For this one, again, we're doing element-wise operations. We don't need the dot for plus because there's no real, matrix addition, whereas there is matrix multiplication and division and stuff like that in math. So we don't need to specify that it's element-wise because it knows it for plus and minus, but we do need to include the dot for multiply, power, and divide because, it doesn't quite understand what you're asking. So in this case, no dot, and every element's going to have 2 added to it. So we're looking at sort of the one above, and we're adding 2 to every number. So we end up with 22, 34, 38, 34, and 22. And again, if you wanted to check this at that stage, you could run it, and you could pop back over here and you would see that that C has been updated to the value of that final line. And you can check that you've gotten it right. So then we've got C1 to 2 equals 12. And what this is doing is it's saying take the first to second elements of C and set their values to 12. So in terms of what that's going to do to our vector, it's going to take the first element and set it to 12. And it's going to take the second element as well and set it to 12. And then the rest will be the same as they were before in the previous step. So we're using range indexing to replace certain values with 12. The next one is C equals C with an apostrophe. So what that's going to do is that's actually going to turn it into a column vector. So previously it was a row vector, now it's going to be a column vector. So if you were to print this, it'd kind of go down the page like this. So basically every value is exactly where it was, except now we've got this vertical orientation, which is much harder to write on the screen. So all those numbers are the same, first element still the first element, second element still the second element, and so on and so forth, except now they're just being flipped around to go from top to bottom. Next, we've got this line of C equals C 2 to 4. So what that's doing is saying we're going to set the value of C to be equal to the second to fourth elements of C. Not sure why it wants to do that. Indenting, there we go. So basically we're replacing the value of C with just the second to the fourth elements. So we're going to take element 2, 3, and 4, and we're going to save those inside C. So effectively we're reducing C down to just contain 12, 38, and 34. And that's all we've got left now. On our next line, we're doing a concatenation. So we're setting C to be equal to C, comma C, which means that we're pretty much putting two copies into two columns. So we're going to have two columns of the same values. So I'll show you what that looks like. We'll have C equals 12, 12, and 38, 38, 38. And lastly, we'll have, if I can hit the right buttons, 34, 34. So we've got just two copies of that have been put together. So they've been horizontally concatenated. And now we've got two copies of the same column. At this point, you might be wanting to check your working again. So again, if you just run it again, you can kind of pop back over into MATLAB and you can see it there. It's also been printed because I forgot to put the semicolon on, but if it hadn't been, you could just type in disk and the variable that you want to check, and you can check that the working you've got is correct. Obviously, you can't do that in the test, but it's handy when you're doing the exercises to check your working as you go. Next line, we've got C, the colon, which means all rows in this case, because it's sort of the first number, is equal to C, all rows, column 2, divided by 2. So let's have a think about how to interpret this. We're saying we want to set all of the rows in the second column to be equal to all of the rows in the existing second column divided by 2. So effectively what this is saying is have a look at column 2 and divide all its values by 2. So we can have a look at what that output will look like. I might just put it underneath for this one. So we'll have C equals 12, 6, because that second column is getting divided by 2. And then our next row will be 38, and that's testing my brain, 29. That's right, isn't it? No, 19, sorry. Thought that sounded too large. And then 34 and, I forgot my percentage sign. And then 34 and 17. So every value in that second column has been divided by 2. So I'll run that just to check my own math, but I think that should be right now. Just see. Yeah, cool, those numbers right. Alrighty, so yeah, that one can be that's probably the hardest one of the non-challenge ones. But just remember that this colon sign represents all. So if you had something like this, that would be saying row 2 all columns, whereas here we're saying all rows column 2. So the position it's in determines what it's kind of taking all of. And you can see in this case, it took every row of column 2 and it divided it by 2. So now challenge question, and I'll do this one in multiple steps so that you can actually see kind of how it breaks down. So we've got D equals sum C all rows column 1 plus C all rows column 2. Then we've used the apostrophe symbol, subtracted 15, and put our semicolon on the end. So let's have a look at the steps. Let's firstly replace our C colon 1 and colon 2 with their actual values. So yeah, let's do that first. So D equals sum, and we'll have effectively, actually this is going to be pretty hard to write because it's still vertical. So we'll have 12 yeah, it's going to be too hard to write, I think. So let's just do it in one step. So we're going to take all rows of column 1 and add them to all rows of column 2. And then this is going to transpose them and make them a row vector rather than a column vector. So what that means is that we're going to have 12 plus 6 as our first element, then 38 plus 19 as our second element, and 34 plus 17 as our third element. And that little apostrophe means that it's now a row vector, which is why I've written it horizontally. So it would have been a bit difficult to write it as columns in this form, but yeah, hopefully that's clear how I got to there. And then we're going to subtract 15 from that overall result. So let's actually reduce that down. So we have 18, 38 plus 19 is going to give us 47.57, and 34 plus 17 is going to give us 41.51, and we're going to subtract 15 still. So then we can apply that minus 15 to every element. So we'll have 3, and we'll have 42, and then we'll have 34. Yeah, I think so. No, hang on. Obviously too much math in my brain in the morning. We'll have 36. Yeah, cool. So then the last operation is to actually add all of those up. So the sum function will go through and convert that to 3 plus 42 plus 36. And that's going to give us D equals 81. So 48, 78, 81. Yeah, cool. So, and again, we can run that to check that I've kind of gotten my math right. So let's give that a run, and we'll just check that I can still do math. Yeah, 81 is our final result. So yeah, we could also kind of, if you wanted to sort of check each step a little bit, like just for your own clarity, you could also sort of actually kind of print some of those values. So you could print like what is C colon 1 and C colon 2, and you can see what those values are. You could also kind of type in what's C colon 1 plus C colon 2 all transposed, and you'll get kind of that intermediate step as well. Then you can add on your minus 15 and check that one. So these are all sorts of ways that you can test and debug your own code if you aren't getting the answer, or if you're getting an answer that doesn't make sense. You can try and, you know, work backwards through your steps. So the main reason I wanted to step it out like this is because if you had to do a question like this in a mid-semester, it's really beneficial to show you're working. Because, for example, if you'd just written D equals 83, then your answer would be wrong and we wouldn't know how you'd gotten to it. Whereas if you'd showed your steps and, you know, you'd made a mistake right at the end, like you'd made this 38 instead of 36, and that had carried through, then we would be able to give you most of the marks. So just show your working steps if there's anything sort of like this, and that'll allow you to get marks where you may not have if you just give it an answer. So it's the same as maths. It's treat it like a maths exam, you know. So that's our warm-up, very long warm-up, I realise that, but pretty beneficial to know how to work with vectors really well. So next up, we've got a question on function scope. So we've got a little bit of code. We've got a function down here that takes two numbers and adds them together and returns the result. And so then in our first line of code up here, we're actually calling that function with the numbers 1 and 2. So it's going to add those up to give 3 and return 3 to result. Then it's going to try and display A and B. But the issue with that is that the script outside the function doesn't actually know what A and B are. The function knows what A and B are, but this code out here can't see what the function can see. Those variables are contained within the function. So it's going to throw an error at this point, and in fact, it's not even going to get to this point because it's going to error at the first line of display A. So to show you what I mean, let's actually create this. So result equals add two numbers, 1, 2, display A, display B, and then actually create that function. Hopefully you can still hear me okay over the rain that's picking up out there. So we'll run this, and there's that ding for an error. So we can see that it printed the result of 3, but then it created an error at A. So again, a bit of a runtime error. It's tried to display a value and then it realized it didn't actually have that value. Also, a little bit of a note on naming where functions are involved. So here you can see that we've written some script and then we've got the function. The name here is not the name of the function, and it has to be that way because we've got script before it. If, however, the function was the thing at the top, then we would have to save the function as add two numbers. It would have to be called add two numbers because the function is at the top. So it'd have to then be called add two numbers, which I've created before, obviously, so replace that. But once you do that, once it's actually named after the function, you can't put script above it. Oop. I must have copied that. All right, result equals add two numbers, 1, 2. So if I tried to put stuff at the top there, then I get an error. So if you want to have script and then function, you have to name it something other than the function name. However, if you want the function at the top and then the script in another file or another function to call it or whatever, whichever the top function is has to be the name. So just two different cases of naming there. It can be a little bit confusing. If you have any questions, just let me know in the comments or via email, but hopefully that's reasonably clear. That's a bit of a detour though. The fundamental point here was that A and B can only be seen by the function that is using them. Out here, there's no concept of what A and B are. We've never seen them before in this outer script, so therefore we can't display them. Normally this is what you want. Normally you want this separation of variables, but if for some reason you want to share variables around, there is the option for global variables. So exercise 3 is all about global variables, and we'll have a bit of a look at how they work. So I might just start by creating this set global function and calling it. So let's set global 3 and create that function set global num global g equals num end. So I'll save this as something else. I'll just replace that untitled from before. So the way to read this is that it says we are creating a global variable g. So anyone that says global g will be able to view this exact copy of this exact variable. So first we have to make that declaration to the world that this is a global copy of g. It's not a local copy of g. So then g is equal to num, which is the thing that was passed in. So for a little bit of intuition on how this is working, if I then go disp g, is this going to work or not? The answer is no, it's not. We're going to get that lovely ding and a big red error. So it says undefined functional variable g. The reason being that we haven't said that we want to use the global version of g. So it's trying to use a local version of g that's local to this script above the function. If we want to share g with the g down here, we actually need to say first global g. So again, we make that declaration. I want to use the global copy of this, not my own local copy. And then when you run that, you'll get that 3. And I might just add a CLC and a clear up here so that the G gets erased every time I run it. Cool, so let's get rid of that for now. So the next line of code we had was to square the result using a function called square. So let's write the code relevant to that. So squared result equals square, and function x equals square global g, x equals g squared. So this is again saying I want to use the global version of g, just whatever everyone else is using, that's what I want to use. If I didn't have this line, so if I commented this out, we would end up with an error because it tries to use a local copy of g, which it doesn't have. So you have to declare global g every time you want to use that global copy of g. So if I run this now, we'll get the squared result is equal to 9 because it's used the global g, which was set to 3 at this point. So here we've set, so let's go global g, disp g. So at this point it's set to 3. So then when we enter the square function, it says I want to square that number 3 and it gives us 9. Now, the last part was to write a cube function as well. So function x equals cube, and it does exactly what it says on the box. So function x equals cube, global g, again saying we're going to use the global version of this function, x equals g cubed, and so then I write the code up here. Cubed result equals cube. Run that. And we end up with the cubed result. So 3 cubed is 27. You could also modify g. So you could, I don't know, add another function called, let's go function increment global. So we would take global g, say, and go g equals g plus 1. So we're adding 1 to the global copy of g. So if I did that before I called cubed result, so let's say I did increment global here, and then display g again, we'll see that we've got, firstly it displays 3 because that's what it's set to by this. Then we get 9 because we've squared that global variable. And then we use increment, which adds 1 to the global variable to give us 4, which is displayed here. And then lastly, we've got cubed result equals cube, which ends up being 4 times 4 times 4, which is equal to 64. So every time you want to use the global, you actually have to say global. You only have to say it once within the scope. So for the script, we only had to write it once and then we could use it multiple times. Same here, we sort of defined it once and then we kind of used it in multiple places. But you do have to use it. You do have to say global before you use it if you want to use a global function. So once in every workspace that you want it to be viewed in. Yeah, so the other thing so if I didn't do that, so if I sort of had another function, just, I don't know, function display a thing, and then went g equals 2 display g, then that's going to actually display 2, but it's not going to change the global g. So I could then go global g display g. Oh, but it's going to, it actually sets the ones above it. That's interesting. I didn't expect that. So if I then display a thing and then display g, it'll print 2 from display a thing, but it doesn't modify the global value of g. Hopefully that makes sense. Local copies versus global copies. Again, if you've got questions, feel free to pop them in the comments. There'll also be the paper-based version of this, which might be helpful as well. So another type of unique variable is persistent variables. So this one asks what would be the output of the following code. So we've got a for loop that loops through and it displays the result of adding 2 numbers 3 times. So the first time it's going to display 1 plus 2, which is 3, then 2 plus 3, which is 5, then 3 plus 4, which is 7. However, a bit of an extension this time is that we've got this chunk of code. So persistent variables are ones that hold their values over multiple function calls. So if we have a persistent n, firstly, when we create it, it's going to be empty. It's going to be just, it's pretty much going to look like this, empty array. So the first thing we need to do is check if it's empty, which means that it's newly created. And if it is empty, actually give it a value. So that's what that's doing there. It's giving it a value of 0 if it's newly created. And then it's adding to it. It's going n equals n plus 1, and it's printing a message that includes that number. So the first time the function's called, persistent will be brand new, so it'll be set to 0, and then 1 will be added to it. So then it'll print that this function has run 1 time. However, when we call the function the second time, it's no longer empty, so it's not set to 0. It keeps its value of 1 from before, so it says n equals 1 plus 1, which is 2. And it then says this function is run 2 times. Then if it's called a third time, it again keeps its value, so it goes 2 plus 1 is equal to 3, and it prints this function is run 3 times. So it might be easier to show rather than tell. I'll copy this code out quickly. There's our for loop, and we have our function of add 2 numbers, which takes two inputs and adds them together. We create our persistent value, which will be empty array when it's first created. So we check, is it empty? And if it is, we do n equals 0, end that off, n equals n plus 1, and print our message. If we run this now, and head over to our command window, you can see it says, it has those outputs we were talking about, 3, 5, and 7 from calling this function add two numbers. And it also has this message saying this function is run 1 time, 2 times, 3 times. Should say times. Now, if I run this a few more times, you'll see that it keeps going up because that persistent variable continues to hold its value until it's explicitly cleared. So you could clear it by having, you could physically set it to another value at some point. So you could set it to n equals 0 once it reaches 30 or something like that. The other way you can get rid of one is to go clear and actually name the file, or clear all, which will clear the persistent values. So that's two ways you can approach that. So that's persistent values. Next up, we're going to have a look at a few different types of functions. So we've got local functions and subfunctions. We touched on this a little bit in lectures, but we'll go through them. So again, both of these are asking what's the output. So first up, we've got the function display average that takes a num array and then calls the average function for num array and prints a message about it. So in the actual average function, it calculates the sum of the num array, divides it by the length of the num array, so it's a manual averaging process. So we'll copy this out and we'll talk about how it works. So we'll actually need to create a new file that's called display average because we have a function at the top, so we have to name it after that function. So x equals average num array, f print f, the average of your numbers is sent to f slash n, and end that off, and then function x equals average num array, x equals the sum of that divided by the length of that. We'll end that off there. So the output of this is going to be, when we call display average 1 to 5, we're going to get 3 because it'll do 1 plus 2 plus 3 plus 4 plus 5 and divide that by 5. So just to prove that point, let's save that as display average and go and run it. So it's going to print that message, the average of your numbers is 3. So it pretty much just, the main function that the file is named after has to be the one at the top, but you can also have functions that belong to this file and can't be accessed by outside files. So for example, I couldn't go over here and try to call average because average belongs to this file. I can call display average, but not average directly. So I'll demo that. So if I go display average 1 to 5, that will work. If I go average 1 to 5, that will not work. So you can see that it's printed the average of your number is 3, but it can't find the functional variable average because it searches by the file name. So it finds this function, but it doesn't see this function. This function belongs only to this file. It can't be seen outside of it. So that's local functions. Subfunctions are a pretty similar thing, except they go inside the function. So here, we can move this one up to here, fix up the indenting, and change it up a little bit. So I'm actually getting rid of this input here. Why can I do that? The reason I can do that is because it's a function inside a function. So we call this a child function. Child functions can actually see their parent function's variables. So this can see num array without actually passing it num array because it's inside this other function. So if I run this now, I might actually need to give it some inputs. It'll work. However, if I had done that before, down here, fix up the indenting again, it wouldn't have worked because we haven't passed num_array to it. So if they're two separate functions, you have to explicitly pass variables between them. If it's a function inside of a function, it can view anything outside. However, this one here, the parent function, can't view stuff that's inside the child function. So if I set g is equal to 2 here and tried to display that out here, the parent wouldn't be able to see it. So the child can see it if it belongs to the parent, but the parent can't see it if it belongs to the child. So why would you want to use one over the other? Well, you would want to use nested functions or child functions or subfunctions, whatever you want to call them, if you do want this behavior, if you want to be able to see the variables that belong to a parent. In many cases, you're not going to want that. Local functions are generally the way to go because local functions allow you to separate functionalities completely, and then you have to pass variables around. So that's typically the behavior you want in order to isolate functionality, but in some cases you might actually want this behavior where you don't need to pass it around all the time for it to be able to see those variables. So that is, I believe, it. Oh no, we have one more. So we've got, two more actually. So we've got function handles and we've got anonymous functions. So function handles are basically like shortcuts to a particular function. So let's have a look at how this works. We've created a variable a, which is equal to @mean. So it's saying that we're going to we're going to use this function, but we're going to just call it a. So it's a reference to the function, but it's just called a. Same with m, we've referenced it to median, and both of these are functions in MATLAB, by the way. So mean and median are both existing functions in MATLab. So we're basically just using these variables as a reference. So then we've said get result a 1 to 3. And if we have a look at how get result works, it takes a function f and it takes a number array. And then it calculates a result based on, add a comment, and then it calculates a result based on the function and the num array. So for this one here, this first one, don't mind my dog shaking in the background. For this first one here, it'll go mean of 1 to 3 because we're passing in a, which is a reference to mean, and we're passing in 1 to 3 as the number array. So it'll calculate the mean of 1 to 3. This second one here, the m of 1 to 8, that's a reference to the median. So it passes in median as f, and the num array is 1 to 8. So it'll find the median of 1 to 8. Here we're not actually returning the value, we're just printing it within the function, so it'll just print out that message. So let's replicate that. So a equals @mean, m equals @median, get result, a 1 to 3. So we're going to expect that to be 2, 1 plus 2 plus 3 divided by 3. And get result m 1 to 8, we would expect that to be 4.5, which is the two middle numbers divided by 2, so 4 plus 5 divided by 2. So let's see if we get the result we expect. F and num array, f being the function, so either mean or median. And print our results. The result is %.2f/n x. End that off. Save it. Untitled for will do. And run it. And there's those two results that we expected to get. So it's a way of shortcutting, like having a shorthand reference to a function. It's not used a whole lot. You'll see function handles a little bit in graphical user interfaces when we get to those in another week or two. But other than that, that's sort of the main place that you'll come across that @ notation. But it's just saying a is now a reference to this function @mean. So the next one's about integer types. So there's actually not a lot on this either, but I've got this little code snippet. So we've got an unsigned integer 8, which means it's got 8 bits of memory and it's not signed. So it's sort of always going to be a positive number. Then B is a int 8, which means it does have a sign. It can be positive or negative, and again, it has 8 bits of memory. And lastly, we have our unsigned integer 16, which has been set to a value of 10. Unsigned integers, again, means that it's always positive. 16 means 16 bits of memory. Now, if we try to run this code, it throws an error. It's already kind of told you in the question. So I'll just type it out and we'll see the error that we get. And then we'll talk about what it means. So we've got all these different types. Question 1 equals a plus b. Question 2 equals a plus c. So when I run this, it's going to throw an error on that first one, the question 1 calculation. And it gives us this message saying integers can only be combined with integers of the same class. So what that means is the integers have to be the same type of integer to be able to be combined. In some other languages, it can do that automatically to a degree, but in MATLAB, you actually have to explicitly convert one type to the other. So if we actually wanted to do this, so part B says, how can you modify lines 4 and 5 using explicit conversion to prevent errors from occurring? So we can actually change one type to another. So for example, here, we can change this one to an int 8. The reason I'm changing A instead of B is if you have a look at these numbers. So this one's an unsigned integer with a positive value. This one's a signed integer with a negative value. So if I tried to convert this to a uint 8, then I would basically destroy the value. I'd destroy the negative and it would come up with some strange number. So I can actually show you how that works. So if I created x equals int 8 negative 8, and if I tried to convert that to an unsigned integer, I get this value of 0 because it treats anything negative as 0. So it just clips it off the end and treats it as 0. Obviously, that's not the answer we want. We want to be actually, have this as 2 and this is negative 8 so that we can do the math. So if I convert this one to an integer 8, then it's not going to change the value at all because positive is also a sign, so it'll retain its value. So I'll show you what I mean by that. So if we have uint x equals uint 8, and I wrote that wrong, and now MATLAB's frozen. There we go. Uint x equals uint 8 brackets 2. If I then convert that to just a regular signed integer, then it maintains its value because it's still a valid value in int 8. And then when I run this code, the error will happen later. It'll happen on the question 2 line. We will have actually gotten a result for this first one if I'd left the semicolon off. So you'll actually get -6 as your answer for question 1. Now for question 2, we actually could convert either of these to the other, but I am going to convert this one to a uint 16. The reason being that although this number is quite small, if it had been large, so if it had been greater than 256, which is the maximum value a uint 8 can hold, so uint 8 can hold up to 255, if it had been greater than that, it would have clipped it. So I'll show you an example. If I had x equals uint 16, 500, so a fair bit greater than 255. So there it is equal to its actual value, but if I tried to convert that to a uint 8, it would clip it to 255, which is the maximum value. So in this case, because it's quite a small number, you could actually convert it either way, but assuming you didn't know the size of the number, you always want to go to the one that's bigger, the one that has more memory, because it basically just means there'll be less zeros in there'll be more zeros in memory. So yeah, this one goes up to 16 rather than bringing this one down to 8. And if I run that now, take off the semicolon, we'll get an answer for both of them that's actually mathematically correct. So that's how we modify that. Hopefully it's clear why we convert the types the way we do. You're not really going to have to do that in this subject, but it's helpful to know for later subjects because definitely you'll run into problems with integer types and memory and everything else when you get into more like hardware. So our last exercise is on floating point numbers and the rounding errors that can result when working with them. So question A asks what would be the output of this code. So we've got A equals, negative 0.2 minus 0.1 plus 0.3. So logically, when you look at that, and if you confirm it with the calculator as well, you'll get the answer of 0. So negative 0.2 minus 0.1 plus 0.3 equals 0. So what you would expect to happen then is, and I might just copy this code out, so A equals negative 0.2 minus 0.1 plus 0.3. A is less than 0, we'll display that the result is negative. Otherwise, we'll display that the result is positive. So based on math, we would expect this answer to be 0, and therefore A is not less than 0, it's equal to 0, which means that the else statement would run. However, what happens in reality is because we're working with decimal numbers, small rounding errors occur. So when I run this, let's have a look at what the output is. The result is negative, which it shouldn't be because it should be equal to 0. So let's do a bit more of an investigation and see what it is actually equal to. So I'm going to do an fprintf and I'm going to print it to 20 decimal places. Oops, got my percent sign. And that \n is just new line, so it goes to the next line after printing. And I'm going to print A. So if we have a look there, not too many slashes, just backslash. So if we have a look there, we can see that it's a negative number, very, very, very small negative number, but it is negative. So that's what's causing this behavior, because it actually is a negative number and therefore it is printing the result as negative. These errors occur as a result of the limited storage a computer has. So there's only so much resolution it can have, given that it's storing all its information as a series of ones and zeros. So what that means is that errors like this can occur. So question B asked, well, how can we modify the code so that we actually get the expected behavior? So in other words, so that it actually displays that the result is positive. So the way that we can do that is we can actually give a little bit of an allowance for error. And this isn't a perfect solution, but it's one of the solutions that you may have to use just to work around the limitations of hardware. So what we can do is we can change this one here to being a small number. So let's say 1e to the negative 15. And to give you an idea of how small that is, I'll print it underneath our other one up here. So negative 1e to the 15, negative 15, sorry. So if I run that, and let's just comment that out for a second so that we can see the difference between the numbers. So now we've got kind of this very small negative number, but in terms of magnitude, it's a little bit bigger than this. So when we use that as our check, what's going to happen is it's going to go, if A is less than this very small negative number, display that the result is negative. Otherwise, display that the result is positive. So this is a smaller negative number, which means it's slightly closer to 0 than this one. So it's going to return false to this check because it's not smaller than, it's actually bigger than, it's closer to 0. So it's going to fail this check and now actually run this. So we'll get the result as positive. Now you might need to use a slightly bigger negative number for different rounding point errors. The error might occur kind of further up. But for this case, that resolution seems to be about right. So you might need to, play around with those numbers and check. But that's kind of how you can work around the floating point error issue. So you can kind of use a threshold rather than an exact equality to just account for those borderline cases a little bit better. So again, not a perfect solution, but it's pretty much the best that you can do when you're working with an actual machine, because they don't remember things the same way you do, and they can't calculate the things the same way that you do. So it's definitely something to be aware of in your assignment where you're doing sort of small time steps. And if you're doing derivatives with, again, small time steps, you need to pick a number that's small enough to give you an accurate result mathematically, but not so small that you start to introduce rounding point errors. because those errors can actually become quite large, as you likely saw in the live demo of derivatives in the lectures. So yeah, just choosing wisely and having a look at your floating point numbers if you are getting some strange errors and unexpected results. That's the main thing to keep in mind. So exercise 11 looks at using the num2string function to build messages. So we're going to create a numerical variable called age and set it to your age. On the next line, we'll create a variable called message and use num2string to create a message of this format. So we want to say the age is, and then have the age included there. And we'll use num2string to convert that actual numerical age to that string. And then on the next line, we'll write some code to display the message. So the first thing we need to do is create the variable age and set it to an age. So let's just set it arbitrarily to 18. On the next line, you want to create your message. And there's a few ways to build the message. So the first one is to just use plus. So you double quotation marks, the age is, plus num2string age. So that's sort of one very neat and tidy way to build it. Another way would be to do string cat, strcat, which is string concatenate, and you can say the age is num2string age. So either of those will work. I might actually just run it at this point so you can see the two different messages. So both of those will work. However, if you were to use single quotation marks, you would start to get some errors. So if I tried to use single quotation marks here, it's actually going to give me an error because it's trying to add the characters for age to the characters for the ages, and that's two different lengths of matrix. So this one has, maybe 10 characters, 10 or 11, and this one has 2. And what it's trying to do is it's trying to combine those. It's trying to do element-wise operations because we've got 2 arrays. That's not what we want to do, so we have to use the double quotation marks to say, hey, we're actually building a string, we're not doing math. And similarly here, if you made this single quotation marks, it's actually going to not include the space. So just make sure you include, when you're doing string building, make sure you actually use double quotation marks to set it as a string. So then the last thing we need to do is just display message. And there you have it, the age is 18. You can change that to whatever you want. And you'll keep getting the same sort of output. So that's handy for displaying messages to a user based on input they've provided or results that have been calculated by your program. So thank you for tuning in, and I will see you in next week's video.